Hello, hello, hello. These set of circuits questions are taken from quite possibly the hardest circuits exam I have ever encountered. The problems aren't impossible, they're just a lot of them, and at least two of them are really tricky. Don't want to give out too many A's, but that was never a problem. This here is a circuit exam question number 2. 20 points. In the above circuit, clearly label each node as VA, VB, etc. 2 points. Identify a ground node, which is 1 point. Based on your choice in part B, indicate any nodes with known voltages and any pairs of nodes with known relationships. So here's what we do. For part A, here's what we do. We just label nodes. Simple like that. So this here is VE. This here is VA. This here is VB. This here is VC. And here is VD. Nice. Part B says indicate a ground node. This guy. That's our ground. Just makes it easy. C, based on your choice in part B. So basically, here's what we do. So we know VD is 2 volts because of the voltage source right here. We know VB minus VC is 4 volts. And because of the ground node, we also know that VE is equal to 0 volts. Boom, boom, boom. Dude, that's 5 points. We got 5 points. So part D for 4 points. Determine the set of linear equations needed to determine the nodal voltages. Clearly indicate each expression. Put a box around it. 4 points. Oh boy. Oh boy. Well, let's do it. Let's do it and get to it. Okay, so let's look at A, and let's just create a node equation for A. Okay, so for A, we have VA. We basically, node analysis is basically, we have currents. You can imagine currents going out of A. Current out of A, out of A, and out of A. So for this is simple. VA minus 0 over R1. VA minus C over R2. VA minus B over R4. And that's it. Boom, 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 boom. Got it. And that's one equation. So here's the other equation. If we go to the circuit and we see this circuit, we see that what would be a good choice? Now, since the problem wants us to do node analysis, we can't do mesh. Mesh analysis would be easy because we have all these voltage sources. It would be easy, but we can't do mesh. It says node. So what do we do about node? Here's what we do. For this guy, it's we have to use a super node. So basically, VB and VC are like one node. Boom, 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 one node. So out of this one node, we have how many currents coming out? We have 1, 2, 3, 4, 5. Jesus. All right, let's just write the equation. So, VB minus VA, VB minus VD over R5, VC minus VA over R2, VC minus 0 over R3, VC minus VD over R6. Boom, boom, boom. We did it. There's your equations. Boom. Full credit. 4 points. Nice. So the last part of the question is part E. It says, determine the voltage across R2, worth 1 point. So to solve this problem, one thing we got to do is that we got to we have to actually solve the node equations that we created. And you can see the problem there. It's like a lot of computation. And, during an exam, you know, we got a lot of things to worry about, and it's like, do I really want to do all this crap just for one freaking point? Yeah. You might have to like, well, we'll do this later. We'll do this at the end. Fair enough. But we're gonna do it right now. So to do this, I'm going to rewrite the equations as, all right, here are my equations. Just 3 equations and 3 unknowns. Unknowns are, if we solve a system of equations for this, just, put in your calculator and let it run, we will get VA, VB, and VC. If we solve this, we'll get VA equals 2.79 volts. And we get VB is equal to 0.151 volts. VC equals this. If we solve the system of equations, we'll get VA, VB, and VC. But we only need VA and VC. I made a little mistake there. VR2 is equal to VA minus VC, and that's just 2.64 volts. And there's your answer. Time for the second part of the question. In the above circuit, clearly label current loops I1, I2, etc. So I guess we're going to do some mesh analysis instead of node analysis this time. B says, based on your choice in part... Oh, it says part B. I meant to say part A. Whoops. Based on your choice in part A, indicate any loop currents with known values and any pairs of loop currents with known relationships. 2 points. Nice. Hey, look, it says part B in the original test. See? I'm not making this up. All right, so for this guy, all we really got to do is just tell the grader, like, do you know how to write a mesh analysis? So let's tell him that we do. So here's the deal. We have I1 going in a loop. I2 going in a loop as well. And I3 in its own loop too. And I4 going in its loop as well. So if we look at I4, we see it's going the opposite direction of this guy. And this guy is supposed to be IB that much. And this guy right here is supposed to be IA. And that's supposed to be 0.0004. So, 4 milliamps. I4 is equal to minus 0.002. This is basically you're telling the grader that, yeah, I understand how this interacts with this guy. That's cool. And now we got to say this. I2 minus I1 is equal to 0.004. So why I2 minus I1? Here's why. This is going in reference with the this guy, with the guy going up, the current source. This guy is going in reference with the current source, so it doesn't have a minus sign. Since this guy is going the opposite direction, it has the minus sign. So the reason why we do this is because of the rules of mesh analysis. If we were using just straight up KCL, KVL, and passive sign convention, if we're in other element constraints, if we're just using those, it could be fair game. But since we're using mesh analysis, we're basically looking at this from that point of view, where we have to follow some rules or else we'll risk having incorrect equations. If we have, like, say we have IK is equal to IX minus IY, we know that this guy right there is the mesh whose reference direction agrees with the reference direction of IK. And in this case, IK is the current source, and the reference direction is going up, and I2 agrees with going up. So that's how we do it. My source is the design and analysis of linear circuits. 7th edition. So after you write those, that's it. You're good to go. Part C. Determine the set of linear equations needed to determine the loop currents. Clearly indicate each expression. Put a box around it. 4 points. We know I4, and we know the relationship between I1 and I2. So first, let's do the mesh analysis for I3. R1 times I3 times, so this is, let's plus R2 R2 times I3 minus I1. Remember, this is going back to what I said about this guy right here. The resistor, this is the resistor reference for this mesh. Is the same with mesh 3. Now that we do this, plus R3 times I3 minus I4, and that is equal to 0. There's your mesh equation. So I could also just write it from inspection. Now, if you watch my video, my mesh analysis video, you can I'll tell you how to do that. But from inspection, it's just this. So all the resistors are in this guy, in this mesh. So it's just this. So you just add them all up. R1 plus R2 plus R3 multiplied by I3. But we know that R2 is shared with I1, so we subtract R2 times I1, and then we also subtract R3, and R3 is connected to I4, so I3 times I4, and it's equal to 0. Those are the same equations. Put a box around it. Now, to find the other equation, well, what are we going to do? Here's what we're going to do. The question is clearly asking us to do mesh analysis. And we know with mesh analysis, if we have current sources in mesh analysis, it makes things a little bit more difficult. So since the question is asking us and basically forcing us to use mesh analysis, it will help if we use a supernode method to calculate the second equation. Basically right here, so if I write from inspection, I4 and R2, and let me just write that. So from inspection, I can write R4 plus R2 times I1, because it's in that loop, and R2 is shared with R3, so I have to subtract R3. Subtract I3. Since this loop shares with the third mesh, I have to subtract I3 times R2. And now I do the same thing for loop 2. R5 plus R6 times I2. And since R6 is shared with mesh 4, we have to say that we have to subtract R6 times I4. And that's equal to 0. And there is your supernode from inspection. The from inspection part, I stress that you must really learn how to do it. You can watch my node analysis video. You can watch my mesh analysis video to learn how to do those from inspection. I strongly suggest that you learn how to do it from inspection, because they will be time savers during this exam. And the reason why is like for this exam is administered in a 2-hour time frame. And the thing is that that's not a whole lot of time, because you're going to come across some real tricky stuff, and that's going to eat up your time, and you have to be smart about how you use your time. So learning the stuff down pat is very, very strongly recommended. So we have these two equations, and that's good. Don't forget, we have these guys right here too. Don't forget those. Part D says determine the voltage across R2. Well, to do that, we have to do what we did before and set up a system of equations to solve. So looking at our equations right here, we have I1 and we have I3, and I4 is known, so we can just move that to this side. And so for this guy, we have I1, I3, I2, and R4. So this has 3 guys. So how about this? We call this equation 1, call this equation 2. And from here, remember this, we'll just call this guy equation 3. So there's your system of equations. So set up the matrix and solve. Just do that. Just set up the matrix and solve. So here's your matrix. So you just put it in and solve. This might take time to input this on your calculator. So maybe you save this towards the end. Like when you have 10 minutes left, maybe you could just save this for the last 10 minutes of the exam. Make sure, if you're doing that, make sure you know it's right. So we know I1, I2, and I3. And we know I4. We know so the voltage of R2, so the voltage of R2 is, that's 4,000 ohms times I1 minus I3. And that's because of this guy, because, I1 through there, I3 through there. So we're taking this from this reference direction, and I3 is in the opposite direction, so that's why you have the minus sign. Because it's relative to the mesh that you're looking at. We're looking at the mesh 1 point of view. Minus 2.5 volts. Boom, 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 boom. There we go.